Okay, so after this short break, let me start again. My name is Tomasz. I'm a staff plus engineer / global product architect at Software One. I've been to our industry for quite a few years already, and during that time, I have built or helped others to build various solutions for various industries on various technologies. And today, together with you, I want to dig into one of those technologies, Azure Functions. From my experience, Azure Functions is actually a very interesting subject of discussions. I have chatted with a lot of people about Azure Functions, and majority of them I can divide in two groups. One is people who, after like a first serious project with Azure Functions, would say, I like it, it's fun, I want to use it again. And the other group is more like, I don't feel it, it feels off, I don't know if I want to use it. What is funny is that both of those groups, very often they justify their position with the same statement. It feels magical, right? And personally, I take such a statement as a problem, right? We are building software-based solutions. They should be based on technology, not magic. If we are basing them on magic, we are setting ourselves on some problems, issues, etc. That doesn't mean I want to tell you not to use Azure Functions. Quite the contrary. I want to look under the hood together with you, so whenever you will be using them, it's no longer magic. If you need, you can go deeper, you understand what is happening. Because personally, I like Azure Functions quite a lot. I think it's a very nice service. It fits certain usage scenarios very well. Not all of them. Nothing is for everything. So I didn't say that. It has nice features, nice capabilities. It's constantly evolving. To be honest, I even like the logo, right? The logo of Azure Functions is one of those very few logos in Azure that are actually telling you what the service wants to do for you. Because what Azure Functions wants to do for us, they want to enable us to focus on the business code, the code that is actually important for our organization or clients, right? The code that we are actually getting paid for. And it promises that we'll run that code in results of all the other events happening in the system, right? Well, that's, of course, a simplification. Our code is never that simple. Our code requires some additional data on the input. It will produce some data. And Azure Functions wants to deal with that as well. Azure Functions wants to take away the integration responsibility from us, allow us to focus on the business code. And that's the part that often feels magical to developers. Because we are developers, we are so accustomed to write integration code. Sometimes we even write more integration code than the business code. Sometimes it's even more complex than the business code. So the moment it goes away, this is some kind of sorcery, right? I need to do that very hard, important thing. So today I want to go deep under the hood together with you to see how Azure Functions is tackling that complexity for us. Because it's sitting in a very specific case. That's the responsibility of triggers and bindings, right? Those are doing that integration part for us. And if we would have like hallway track conversation about Azure Functions, somebody would probably say there is a lot of integration, a lot of different services that you can use. The truth is that Azure Functions, as they are, deployed in Azure, run locally in containers, they support only two things, HTTP and timers. That's all that is. All the other integrations that you may know, Cosmos DB, Service Bus, different kinds of storage, even durable functions, those are all extensions. You get those extensions into your applications, depending on the language, that's either like direct reference to a package in .NET or some definition in host.json in different languages, right? So in order to truly understand triggers and bindings, we need to understand those extensions. And you can probably already guess, there is quite a few things in there because that rectangle is quite big. That means I can put a lot of smaller rectangles in there. And this is exactly what you're going to do. I'm going to start with the stuff we have already named, bindings and triggers, right? This is the stuff that manifests itself outside. If we are .NET developers, we interact with this directly. We have attributes coming from those packages. We apply them to parameters, return values. This is how things works. If you are working with different languages, in Java we have annotations, we have definitions in functions JSON. They all boil to the same concept, representing that attribute. And the core of that integration responsibility hides in those two components. So how they look inside of Azure Functions? Let's start with bindings. Bindings are responsible for integrating data on the input and on the output. Internally, they are represented by something called binding rule. and that's just a mapping container. It maps that attribute that represents the binding outside with different components responsible for integration. That can be either value binder. Value binder is responsible for in or in and out integrations. And those in and out ones are something that you are very unlikely to see, right? This is basically heritage of programming languages that generally support in and out parameters, but we no longer use them, right? That often, at least. And in Azure Functions, you can do the same thing. You can get a value on the input, modify it during the execution of the function, and it will be updated on the output when you're finishing your function. But generally, we don't do that anymore, right? We want our code to be clear, readable, so we want to return our data explicitly. And there is a separate component for that, asynchronous collector. And basically, from like bindings, from input and output perspective, this is all there is. Nothing more. 4 rectangles, 3 arrows, right? Looks simple, because it's a diagram, right? And diagrams are for architects, so they can simplify things, right? Later, developers come, they have to implement something, and problems arise, right? This is why it's the best to be a hands-on architect. You can first lie to yourself with a diagram, then you sit together with the team, you suffer the problems, right? So that's perfect. So in order to understand what is actually happening there, we have to take a look at the code. The code has to be .NET C#. That's the language of extensions. We're not going to be caring for any specific syntax details. We care about the concepts that the code is expressing. Let's start with that attribute, because that's the entry point. And usually with the attribute, nobody is expecting any kind of problems, some strange things, right? Because attribute is simple. You can decide where to apply it, parameters, return values, and it has properties. That's all what there is. Those properties are what we know, right? This is where we provide values when we are configuring our functions, writing definitions. The trick is that the moment you start looking inside Azure Functions because you want to understand something, you can notice that this attribute is getting to use in various different ways, which doesn't make sense, at least at the first glance. Because Azure Functions is seemingly transforming that attribute depending on the context that you are in. And there are 3 main contexts in Azure Functions. The global one, that's the one that binding rule exists in, right? All the definitions, etc. Function definition one, that's the one we as developers interact the most. We are defining our functions, what they are supposed to do, how they are supposed to work. And the invocation context, the one which is actually most important for the Azure Functions, and we usually doesn't see it. And the difference is that, as in the definition context, we are providing some values here, we will notice that in the invocation context, those values are completely different. And that's the result of those different decorations on those properties. If we have an upsetting decorated property in Azure Functions, that means that during definition you have probably provided some kind of a key that reaches to settings, etc. If you look at the code that is touching this parameter in the invocation context, there will be ready to use value. Azure Functions will pull that for you. The same for the auto-resolve one. In the definition context, you would usually put an expression there. A typical example, you have an HTTP trigger, and you have an additional input binding that, let's say, is grabbing something from the database, and you want that item to be grabbed by an ID from that URL. So you write an expression that is parsing that URL. And Azure Functions, for the invocation context, is automatically calculating that. So there is a ready-to-use value. And that's actually important to know if you want to look deeper, understand deeper, because that is reflected in all those integration components where it's hiding that logic that you are interested in. Let's take a look at value binder. As I said, it's responsible for in or in and out integration. It has 2 methods, get value, set value. Makes sense. What might not make sense for you, at least when you look the first time at it, that there are no parameters here. I mean, there is a value for that set value, but nothing about the context. So how does it know which functions it's getting value for? Well, the answer is that value binders always live in that third context, the invocation context. They are created for a specific invocation. And that has consequences, because that means there can be quite a lot instances of them, as many as parallel executions of the functions. So they contribute to resources consumption. They also contribute to latency, right? Because they have to be created, destroyed per every invocation. So they have to be truly lightweight. all the state, so all those values from configuration, from option, this attribute, any hard processing or state management, like any complicated logic, connection pooling, caching, it has to happen outside. If it would be happening here, functions will be 10 times slower or even worse, right? So this is why we have that important third context to actually be able to inject that very quickly when this is constructed. The same comes from asynchronous collector. In fact, you can experience that firsthand if we are .NET developers, because in case of .NET, you can ask for a parameter of type of asynchronous collector. You will have direct access to that add method, right? This is usually how you return multiple values from your functions. But if you are not doing that, you are just returning a value or you're using a different language, Azure Functions will create this for you, call that add method. So whenever you are interested of how Azure Functions is integrating your output data, just find that asynchronous collector, go to the add method. It may have different levels of complexity. If it's just a queue under the hood, then probably just inserting an item. If it's a database, then integrations with databases, usually they can do insert, update, and create structures. Containers, tables, they do that. So whenever you want to actually know what they are doing, how they are doing, what is the logic, just find that method, take a look. It's on GitHub, right? So now we have a gap, right? We have those components which are responsible for integration, and they are in the invocation context. And you have that binding rule, which is global. And you have arrow, the greatest simplification in all of the designs, right? Arrow. What that arrow must be to actually be able to go from that binding rule to something that is being created per every invocation of the function, right? That arrows must represent something that is able to create a significant amount of those objects quickly. And we have a solution for that, a pattern for that, factories, right? So what those arrows actually represent are factories. What is actually registered with the binding rule is factories. And there are multiple ways of registering that factories, and there are two important ones. One is a generic factory. And it's a nice factory because it's enclosed in a type, so there's a place to separate logic, encapsulate state, do some testing, but it comes with a price. The registration for a generic factory is that first one, bind to input, requires providing a generic type parameter. And Azure Functions will use that type parameter to actually validate if the binding can be used for a specific function definition. That means this parameter provided here must somehow match to the parameter used on the function. If they don't match, matching is a hard word, we're going to get into details how they can match, then Azure Functions will say, I cannot start this function, the binding doesn't match the definition. And this is often a very serious limitation, especially if our input is something that can return JSON. So extensions author would like to be helpful for the developers, be able to basically deserialize to anything. So in that case, this is where that second way of registering factories comes in, something that doesn't have no limitation, bind to value provider in this case. We are getting a lot of flexibility for a price of complexity and simplicity at the same time, because that second type of factory is just methods, and methods are not perfect to represent something potentially complex, because first question is always, where did the extension author put that method? And there is no rule for that, so finding it may be a little bit harder. Also, methods are not great for like encapsulating state, right? That's a problem. Encapsulating logic, testing if they are private somewhere, right? And those methods will be more complex because they have to deal with that support of multiple types. So they usually contain some reflection, right? That's the .NET mechanisms for that. And that's hard to interpret. That's actually stopping us from getting where we want to the actual integration code. Luckily, we don't have this problem with the asynchronous collectors. They support only that generic registration. The trick is the first time you will take a look at this factory, you will be surprised because it's a converter. That's a typical factory interface, right? But it does the same thing, roughly. We have the type of the parameter. That's the generic type. We have that attribute in the input, in the invocation state, and it is supposed to produce an asynchronous collector as a result of conversion. Unusual interface, but works as a factory. But we have now this problem of limiting that type that can be used by a function. And Azure Functions has a, let's say, very tricky solution for that. As you can see on that snippet, and all those snippets that are coming from a custom extension for RefingDB, and I doubt you ever used RefingDB. Anybody did? as expected. I once worked in a project when we were moving some stuff to the cloud, and RefingDB was crucial, and it was nice for running in containers, and we write a custom extension for it to be able to use Azure Functions with it. And you will probably be guessing that this RefingDB open type, it's something to do with RefingDB, right? The name suggests that. The trick is that the important part of the name is the second half, open type. Open type is something very specific in WebJobs SDK and in Azure Functions SDK, because Azure Functions are built on top of WebJobs, SDK are built on top of each other. Open type is something that in certain scenarios for Azure Functions means T at runtime, generic, anything, basically. If Azure Functions sees open type, fine, I can think anything. And you can further deliver from open type to narrow that. There's one ready-to-use option, opentype.poco, and it's no longer anything. It has to be an object with properties, and extension authors are delivering further, building logical conditions for those types. So if an extension author was able to express the requirement for the type supported by the binding in a logical way, it will be here. And Azure Functions will evaluate that isMatch method when it's reading the definitions of the functions. If it returns false, Azure Functions cannot start this function because the definition doesn't match the binding. Right? That's the almost exact error message. If it's true, fine. We are assuming that the extension author knows what he was doing. It will work, right? So those concepts, those value binders, asynchronous collectors, those factories, this open type solution, let's call it like this, they are what actually makes up bindings. If you understand those concepts, you can actually go to GitHub, grab any extension, read it code, you will understand what is happening under the hood. But bindings are a little bit less important. I don't want to diminish them. They are very important. But what is more important is triggers, right? If there wouldn't be a binding for a specific service, we are still fine. We can use SDK in our function, connect to it, use it. It's just not that clean, right? Without triggers, nothing would really work. I mean, we can try to base things on timers. I don't know if I would Azure Functions for that, right? So triggers actually are the thing that makes function make sense. And triggers are more complicated than bindings. They start kind of the same because there is that attribute, there is that binding rule, but triggers have to actively deal with both of those further contexts, the definition one and invocation one. For the definition one, they have a trigger binding, which is responsible for creating the definition of the trigger for the definition of the function. What that means? They have to create a couple types, like descriptor of the invocation, value provider within an optional way to provide the value for the invocation, and that most important part, listener. So that part that is actually attaching to our service, listening for the events, causing invocations. And even on a diagram, it's no longer as clear as the bindings was, right? So once again, we are digging a little bit into the code. How that trigger binding is creating a definition. First of all, it has to define what is the type of the trigger value. And trigger value basically represents the event that is coming from the service. It has to be a very specific type, only one. It doesn't have to be the type of the parameter on the function. There are ways to convert that. One of those ways is this value provider that can be created in that bind method. That bind method is being provided that value as an object here that we have just defined, the binding context, and it can create a value provider to be used to transform that event object into something else. It not always makes sense because it's per invocation, so it's expensive. And once we take a look inside, I will tell you when it makes sense, when it doesn't make sense. The thing you always have to create is that listener, and you always have to look how that listener is treating that factory context, because that's the most important thing. It contains the executor. Executor is the API for triggering the invocation, providing the data. Last but not least, parameter descriptor. A descriptive way of telling us developers what has been invoked and why. It has to contain the trigger name, parameter name, all the other potential attributes that the author decided are important, and it needs to nicely format it in a string for us, so we can read it. You can actually meet those strings in console if you are running Azure Functions locally. They will pop up. They are there in the logs. They are for you to actually understand when which invocation has happened. So let's dig a little bit in those two last components. Value provider. As I said, it's an optional way for transferring that trigger value into something different. And it lives in the integration context, and it has the same characteristics as value binder. Because it's being creating per invocation, it actually already gets a captured value that is supposed to transform. It needs just to tell Azure Functions to what type it's transforming, so that type can actually be validated with the parameter, not the trigger value. And it can use whatever is there in the integration context to transform that value. And that's actually the only thing that makes sense to use them, if you need that integration context. If you need access to the database, queue, whatever there is, to any of those services, any of the state. So for example, you have an event, but you want to query something from the database to have some additional metadata, enhance it, then it makes sense to use it. If you don't require that integration context, don't. There are better ways, more efficient ways, which are not using resources per invocation. And you will see that in every extension, that other way that we're going to get to is a lot more often used than this one. This is only for special cases. Now, the listener, on the other hand, it has to be there, right? It has a typical API of a background service in modern .NET. If you have been working with .NET in different contexts, let's say ASP.NET Core, you have been writing hosted services, the same API, right? Or you have been generally writing background services in .NET as application using the worker template, the same API, right? That's pretty standard API for an in-memory service with a full lifecycle. So when you are looking to understand what is the actual trigger characteristic of the extension you are using, because that might be important, that creates limits for you, you need to find that start method. It will contain usually two blocks of logic. The first block will be the state management, because we are talking Azure Functions, highly parallel environment, a little bit fragile. Things can happen. Those lifecycle methods can get called multiple times. So you will always find in all of them some state management to protect from being called multiple times, because if they wouldn't, bad things would happen. Something as mild as just wasting resources for having multiple connections, or something as serious as executing functions multiple times for the same data. So only after that state validation, there is the actual logic when you can learn what particular service is doing to get your data for you. What is it using some kind of SDK? Is it using pooling? If yes, what options you have to actually play with it? What limitations are hard-coded? Whenever you are in doubt, you can go there, read that, know exactly what is happening. Basically, everything can be happening here. The only limitation is it has to be asynchronous. It has to return task. That task represents the listener to the Azure Functions. Whenever Azure Functions decides to shut down a listener because, I don't know, we are scaling down to 0 or something, it will tell you to stop, cancel. So an extension will detach from the service, clean up, stop that task. To wrap up the triggers, we are missing that one arrow between the binding rule and the trigger binding. As you're already expecting, it's a factory. In case of triggers, those factories are quite simple because they have one job to do. Try to create a trigger binding for a function definition. There is a context. In that context, there is a parameter. In that parameter, there is that attribute. In definition context, so that's a unique place that you will actually see the extension code calculating those values from the settings, from the expression, passing them down so they can be cached. But generally, there is not too much complexity here. Because a lot of the complexity that we could expect here is actually extracted to those additional components that fill up those rectangles. Because if all the code would have to go to this, that would be really cluttered, right? Except of integration, it would have to be doing other things. So there are other components like validators and converters to actually take some weight away from those components. They are also registered with the binding rule. Converters can be registered as either specific types or open generics. Every registrations tell Azure Functions which two types can be actually converted. And this is the efficient mechanism to cover that gap between the types that triggers, input, supports directly, and different parameters of the function. Because when Azure Functions is making that match check, it will look for converters. If there are converters, it will happily use them. So this is the way to extend the number of supported types. Validators, on the other hand, they are there to take away the responsibility of validating the definition of the function. There are simple methods. They are being given the instance of the attribute for that definition, type of the parameter, and any cross-validation on that definition can be done here. If there are some properties which values depend on other properties, here. If there are some properties which values depend on the type of the parameter, here. If those validations fail, Azure Functions cannot start the function definition doesn't match the bindings. So now we know there is a bunch of other stuff in that extension, right? There are bindings triggered and some supporting types for them, validators, converters, and those services I was mentioning that are doing the heavy lifting. What we don't know, if we actually want to understand a specific extension because we are using it, is how to start going through that. Right now, this is all tangling in the air, right? How to configure such an extension? There is a specific entry point for every single logical one. That's the extension config provider. It has to be decorated with the identifier of that extension, and it is the point of contact between the logical extension and Azure Functions, because this is being created from dependency injection container. So it can ask for dependencies through constructor, configuration, option, services. It can later use those dependencies in the initialize method. This is where those binding rules are being created. So all those dependencies can be captured, passed to those factories. That obviously has a consequence because everything which is captured here becomes a singleton. We don't like singletons, especially in a highly distributed environment, because that means there needs to be a lot of code dealing with parallel execution. If you are doing connection pooling, caching, that becomes problematic. And you will notice in those services that this code is usually complex to handle that. There's also one more thing that can be done here, and that's once again registering converters. And what's the additional values of registering converters here? Well, it enables a certain trick. And I'm using the word trick because it can be magic if used not properly. The technology under the trick, which is named extending other extensions, is the fact that there is one global converters manager in the entire Azure Functions app instance. What that means is that converters registered by a single extension can be seen by another one. What that means is that, let's say you have a function, and you are using a certain binding, and you have a ton of business code, and actually your business code requires completely different type than the binding supports. So you usually have some conversion code in your function. And that conversion code, if you are unlucky, can spread across your functions, right? So you will want to extract this, and you will create some static utils or something. And that's not nice, right? You can extract that code to a converter, wrap that converter in a very small extension because it doesn't have to have anything else. It can be registered globally, no binding rules. Install that extension. The extension you have been using for the input will see that. You can change the type of the parameter of the function, and it will just work. Of course, if you don't document it properly, it will be magic. Nobody who is not intimately familiar with Azure Functions will figure it out what is happening. So if you are using such mechanisms, which are in the bigger solutions quite useful, document them so people know what is happening on. So we have that entry point to a particular extension. If you would like to start with a code base for anyone, you are missing just one more entry point, the entry point to the entire assembly. That's the WebJob startup class. It has a single method, configure, a builder. That builder has a more or less typical dependency injection API. You are registering your extension config providers here, your configuration, your services. This is how it works. This is actually almost makes that complete. This is actually enables us to track the entire path of those extensions where Azure Functions is starting up. Let's say we have a function up. We brought some extensions, we usually do. We deployed it to Azure. Azure is starting our function up. The Azure Functions runtime will scan all those extension assembly for those WebJob startup classes. It will call the configure method, register or extension services. It will then ask for all the extension config providers, call the initialize, create all the binding rules. It will then scan all the functions definitions, match to the binding rules, trigger bindings will be created, that will create trigger listeners. They will be listening for events. Events will come, hopefully. Invocation will happen. That will go back to to the binding rules, get value binders, asynchronous collectors. We have our entire integration stack. If we want to, we can understand how it works for a particular extension because it's no longer magic. So we are happy, we are understanding our solution, we can go to production. It will work or not. Various things can happen, right? We are developers, we are responsible for writing code, right? Azure is responsible for making it work. But when we are doing that, when we are deploying this stuff to production, somebody will most likely come. That somebody will be either an architect or tech lead or some more experienced person, and part of his job is to make everybody feel safe, right? Regardless if they are safe or not. The way that person is doing this is by asking questions and getting answers that make everybody feel comfortable. And those can be different questions, more or less matching the situation. I mean, you can have a standard list of questions. Regardless of the approach, there is usually one question that always comes up, right? Whether it makes sense or not. Will it scale? And when asked this question, what will we answer? Well, it will. How? That's Azure Functions. Microsoft is telling us in the documentation that it will scale up to demand. It will be fine. It's magic. OK. So we go to the production, and it doesn't scale. Or it scales in a way that we are not expecting it to scale. Why? Because we trusted the magic, right? And that's the consequence. It would be better to actually understand what is happening. Can we understand what is happening? Well, how Azure Functions are scaling? Azure Functions have a component. It's called Scale Controller. It's not part of any of your function apps. It's there in the overall infrastructure of Azure Functions. Based on the function's definitions from your function app, it's attaching itself to all those different Azure services, monitors, queues, databases, what is supposed to be done there. Based on that information, it decides how many instances of your function app it should create. That's the unit of scale in Azure Functions. Single function app. More scale, more instances of the function app. Less scale, less instances. And that's all. That's how it works since Azure Functions version 2. And that's actually problematic, because that's still kind of magic. First of all, we don't know exactly how Scale Controller works. It has heuristics, obviously, but we don't exactly know them. So as every magician, it can perform only the tricks that he has learned to perform. If there is anything in that function app that he doesn't know, and that is basically every custom extension, there are even 2 extensions from Microsoft that he doesn't know anything about, RabbitMQ and Kafka, because they doesn't match directly in anything in Azure, so what it can do, it will not do the trick. Also, as every magician, it will not do the trick if we break the scene that it has prepared for the trick. And how we can break the scene? We can make a proper infrastructure around this. If you wrap Azure Functions in virtual network, as you generally should in most instances, you put up firewalls on those services, use private links, private endpoints, Scale Controller goes blind. It can no longer do anything. It will not scale anything for you. And that's a serious problem, and Microsoft acknowledged that problem. Microsoft is even trying to give us 2 solutions to that problem. We already have one. The one which is coming with the Flex Consumption Plan. It will be exclusive to Flex Consumption Plan. In Flex Consumption Plan, when Azure Functions app is being deployed to virtual network, Azure Functions will deploy an additional component. Trigger Monitor, it's named, just not to confuse anyone with anything else. And that component will be responsible for reaching to those services, feeding the data to Scale Controller. Scale Controller will be able to scale our function app. What we already have is that something that Microsoft enabled in 2019, they figured out in 2019 that there are, in fact, those extensions, and they are already doing a lot of integration stuff. They are always connected to those services. So maybe they can participate in gathering metrics, voting how to scale. And later in 2023, so last year, Microsoft also decided maybe they can tell how many workers they would want. After all, they know what they are doing, probably. So now there is an option for those extensions to feed the data to Scale Controller, metrics, votes to scale, how many workers they want, and they can be responsible for monitoring those services. I'm saying possibility and can because that's not the default option. It's not there for the consumption plan. Well, in consumption plan, things can scale down to 0, so there will be nothing to host that code. It's only for the premium plan. Additionally, Microsoft motivates that this is a solution for scaling in virtual networks. And until flex consumption, only premium supports virtual networks. So this is why it's there. And it's not there by default as well. You have to turn it on. And when you turn it on, you get that unique possibility of actually understanding how your function is scaling down to every single heuristic. Because back, it's in the code that we have access to. It's on GitHub, right? And we can find that code in the extension and read it. It's attached to listener, so we already know where that is. If a particular extension is participating in that scaling mechanism, the listener will have methods to return two additional components, scale monitor and target scaler. Scale monitor is that older component. It's responsible primarily for gathering metrics. How does it gather metrics? That depends on the service, obviously. I will use Cosmos DB as an example, because we seem to like it on this conference. So in case of Cosmos DB, the trigger is based on change feed processor. And change feed processor has a change feed estimator. So this code is actually creating an instance, asking for the information. The information contains how many items are there waiting to be processed, and how many list documents are there in the list container. And list container is something that is managing state for the change feed processor of Cosmos DB, right? Very internal knowledge to Cosmos DB. That's the advantage, because the people who are writing the Cosmos DB extension, they knew Cosmos DB. Surprising stuff. And this will be needed, because once in a while, when a scale iteration comes, the scale monitor is being asked to vote. It's being fed back all the metric it has gathered, provided to scale controller, and it's supposed to cast a vote. And the vote can be scale out, scale in, neutral. And what Cosmos DB extension does based on those metrics? Well, it looks at the sample. If the sample is small, it will say neutral. I don't know enough, I don't want to do any harm. If the sample is big enough, and the number of remaining items is growing, always very high, scale out. Unless the number of existing workers is already equal to number of the list documents. And we are going into internal knowledge of Cosmos DB again. The way change feed processor works is it's very nicely prepared for parallel processing, but the upper bound limit is that every parallel client needs to own at least one list document. So if we have more clients than list documents, we are basically wasting resources. They will not process anything. So the Azure Functions extension knows that. It will not scale beyond that. What's more, if Azure Functions extension for Cosmos DB will notice that that container has been restructured, once again, internal Cosmos DB knowledge, it will vote to scale in regardless how many items there is remaining. And it obviously will vote to scale in if the number of items is falling or is very low. If things are steady, it will vote neutral. That's more or less the heuristic for Cosmos DB, but what is important, we can go to GitHub, find the extension, understand that heuristic in details. That other component, the target scaler, is actually that newer one. It's responsible for providing an exact number of workers that the extension would like to have. And there are different heuristics for that. Cosmos DB has actually a very simple one. It's saying that at minimum, I want one worker per 1,000 of items remaining. That's my minimum. That's what I want, right? There is also a certain Azure Functions functionality that is being often implemented here. It's named dynamic concurrency. And if you read documentation, it tells that this is a way to limit how many items is being processed in parallel by a single instance. When it's implemented here, this is actually what a lot of extensions are doing, it's being implemented as a simple division. So let's say dynamic concurrency is 100, there is 1,000 item remaining, let's divide 1,000 by 100, that gives us 10. If we get 10 workers, we are happy because theoretically, every worker will process 100 items. Will it? Will even that extension get 10 workers? Not necessarily, right? Because there are other conditions, and the step in a scaling iteration is +4, -4, so it certainly will not get there immediately. But what is the biggest value for us as developers is that this runtime scaling capability is sitting in the extensions. If we are using it, we can analyze it, very carefully understand how our Azure Functions should be scaling. on a level of a single trigger, single extension, and the level of the entire function app. Because, as you could notice, that scaling mechanism is attached to a listener, right? And how many listener is there in every function app? As many as triggers, right? So let's say we have a function app which has a Cosmos DB trigger in it and a service bus trigger. And there's a lot happening on the Cosmos, very little on service bus. The Cosmos trigger will vote, scale out, scale out. Service bus, scale in. What if we have a lot of triggers? Where if there is a lot of entities allowed to vote, and they have different needs, bad things can happen, right? So if you are seeing that your function app is scaling in some erratic way, not what you would think makes sense, it might be time to actually analyze characteristic of every single trigger, what's the data input, and maybe change the granularity of your function app. This is when those low-level details that we are usually not exposed to impacting the architecture of our solution. In fact, the Flex consumption plan intends to fix some of that, only exclusive for it, not for others' plans. It's bringing per-function scaling, not for all the triggers. For example, not for HTTP, I believe not for durable function, and something else, I think. But for others, it says it will orchestrate that. It will actually put that function up on different instances and scale those instances depending on the trigger it has chosen for those instances. So it's going to try to handle that, right? There are some caveats to that, but it's better than nothing. And from like big picture perspective, this is all. We have went through that entire integration responsibility and its consequences to our design. Well, there's one small elephant left in the room, the isolated worker model. The isolated worker model is something that has been there for all the languages except .NET since Azure Functions version 2. For .NET, we have it from like 2020, something like this, something around .NET 5, .NET 6, right? And soon we will have only it for .NET. Microsoft already announced November 2026, end of support for Azure Functions .NET in-process model. Done. That means that in 2026, all the languages will have the same situation. We have two processes. One for the function host, the other for the isolated worker, which is running our business code. And those processes are communicating. In case of .NET, that's gRPC, which is nice, more performant. Other languages usually have to stack with HTTP. And all we have discussed so far, all that integration capability, it sits in the function host. In that case, what sits in that isolated worker? Well, depending on language, there are different mechanisms to actually represent those bindings. In case of .NET, that's new extensions, let's say. But they are all just bridges to those in the function host. How they are making that connection? Well, that depends on the language, right? In the case of .NET, that's actually very developer-friendly. There is a direct information in that assembly to which in-process extension it is mapping with an exact version. And the tooling will handle all of that for .NET developers. Lucky them, right? In case of other languages, that's host.json responsibility. There is a simplified way of registering extensions from Microsoft. There's like a single line that you can put to get the Microsoft bundle. But if you have something custom, you have to manually play with host.json so it is able to drag it from somewhere. On top of that, there needs to be a mechanic to get in those definitions, right? We have on our functions. In case of .NET, new attributes. In case of other languages, those annotations in Java, those definitions in functions.json. In the end, they all get serialized, so they just represent some DTOs, send over that connection, and the functions host will recreate the attributes for the in-process extensions, find the proper binding rule, the integration will start happening in the function host. The input payloads for inputs, for triggers, output payloads for outputs, they will all be handled there. And they will be sent across that communication channel, right? And that's a limitation. Because there are certain bindings, there's a lot of them in .NET, but there are also in other languages that support very specific types, SDK types. Like, I don't know, client to a database, client to a queue. You can't send that over gRPC. That doesn't work like that, right? So what actually Microsoft had to do to enable that, and this is why we still don't have a parity in .NET between the in-process and isolated worker, is that there is some kind of mechanism, different for every language, to run some of the integration code in that isolated worker model extension. In the case of .NET, once again, converters, right? In other languages, different mechanics. They can usually be in every language attached to inputs or triggers, and they can take over the process of that sending over the wire to get the value, right? They can use whatever they have accessible given in given language. In .NET, in fact, those assemblies can register their own dependencies, services, etc. Based on that, they can create the value for a function locally. They shouldn't have like long-living connections, etc., but they can connect something like a database client or something else, inject that directly to the function. So that enables for isolated worker model the SDK types, and also that architecture of isolated worker model is the source of all the limitations that we had things in in-process model that actually not always can be done in the isolated worker model. And that, in fact, covers the entire subjects of trigger and bindings on, let's say, after all the code I showed, I don't want to say it, but high level. Okay? There's more details, and somehow you are interested in that. The first link, it contains a series of articles that are going into details of those different things. The second link is my small polar bear. It's that RefingDB extension. It's actually simple enough that if you want to go through code of it, it will show you more the concepts than the actual RefingDB-related stuff. So it's nice if somebody wants to talk about it in context of a code. I think I'm right on time, so in that case, thank you. Thank you for your time. I hope you will find this knowledge useful. I strongly encourage you to look one level deeper to understand what is happening under the hood, and who knows, maybe you will have to write your own extension.